Hello, I'm Suzan Ejada. Today I will be presenting our work with Professor Erhan Öztop and Professor Emre Uğur titled Diffusion Policies for Out-of-Distribution Generalization in Offline Reinforcement Learning. Offline reinforcement learning focuses on learning a policy from previously collected datasets without the need for real-world interaction. This approach can be particularly beneficial when interacting with the environment is expensive or risky. The dataset represented as D consists of MDP tuples generated by a behavior policy that can be suboptimal, denoted as pi beta. Each element in this dataset is a tuple of state, action, next state, and reward. By using this pre-collected data, offline-RL avoids the need for further data collection, which can be both costly and unsafe in many real-world applications such as robotics, healthcare, and finance. The aim here is to improve upon the behavior policy that was used to collect this data. The challenges of offline reinforcement learning are the distribution shift and uncertainty estimation. Since state and action distributions in the offline dataset can differ from those encountered in the evaluation environment, generalization in out-of-distribution state and action samples is a prominent topic in offline-RL. The idea here is to build systems that are capable of adapting to unseen or unexpected conditions. In real-world offline-RL applications, models often encounter situations that are not in the training data. How well they generalize to these OOD scenarios is crucial for robust performance. Generative models like diffusion aim to generate new samples by learning the underlying probability distribution of data. In the context of offline-RL, where datasets may be collected from multiple agents, diffusion models are particularly well suited to capture this multimodality. However, there is a significant challenge when used in offline-RL. Diffusion models can become unstable in OOD state regions. This instability arises because these models might struggle when they encounter states that were not adequately represented in the dataset, leading to unreliable policy decisions. Enhancing OOD generalization is crucial for learning policies that are robust and adaptable, especially when dealing with unfamiliar or unexpected conditions in real-world applications. To address this challenge, we introduced State Reconstruction for Diffusion Policies, SRDP, that integrates state reconstruction learning into diffusion policies. Using state reconstruction promotes representations that generalize more effectively to OOD states. By this way, the policy learns a more complete understanding of the environment, allowing it to adapt better to unseen conditions. Diffusion models are a class of probabilistic generative models that seek to generate new samples by learning the underlying probability distribution of the data. The forward diffusion process follows a Markov chain to slowly destroy the structure of an original data sample, x0, by adding noise to obtain a sequence of noisy samples, x1 through x capital T. Since the sequences of noisy samples are available during training, we can train a neural network to predict the noise epsilon t at a given time step. The structure of the posterior qxt, given xt minus 1 at each time step, is not learned, it is predefined. Here, the distribution of the latent at final time step capital T is an isotropic Gaussian distribution. We can generate samples through an iterative denoising procedure in the reverse diffusion process by using the predicted noise at each time step. The joint distribution of the reverse diffusion chain is denoted by p theta of x0 to x capital T. The simplified denoising diffusion probabilistic model loss function for diffusion time step t is given by LT. Here, epsilon theta is the noise predicted by the neural network, and epsilon t is the true noise used in the forward process. Diffusion Q-learning uses a conditional diffusion model to generate actions that are conditioned on the state. The reverse diffusion chain, conditioned on the state S, is represented by pi theta, and T refers to the diffusion time step. Actions A0 generated through this reverse diffusion process is used in Q-learning and policy learning. Diffusion Q-learning updates the Q values using double Q-learning trick and Bellman operator minimization. In our work, we update the Q values similarly to evaluate the improvement from the state reconstruction signal. In this section, we focus on the architecture that enables our approach to generalize better to OOD states, starting with the shared representation layer. We leverage a shared layer that helps the model generalize to OOD states, particularly those that are close to the latent dimension manifold. This shared layer encourages robustness through regularization, making the policy adaptable in unseen states. Next, let's talk about the fully connected module denoted as F5. This module is responsible for mapping the noisy action, the time embedding, and the state into a shared representation, Z. This mapping allows the model to handle complex dependencies between the action, states, and the time in a more structured way, improving its capacity to generalize in OOD states. Autoencoders are powerful tools for reconstructing OOD samples. Specifically, when OOD samples are near the latent manifold of the training data, they tend to have a low reconstruction loss. This makes autoencoders particularly useful for reconstructing OOD samples that aren't too far from the model that has already learned. The goal here is to minimize the difference between the state and the reconstructed state. We map the input noisy action, state, and time into a shared representation Z using F5, as discussed in the previous slide. This shared representation is then passed through another module, FPSI, that specializes in reconstructing the state. We minimize this loss function, LR, which measures the distance between states predicted by our reconstruction module, FPSI, and the actual state. The diffusion head, F theta, uses the representation Z to predict the source noise that determines noisy action at diffusion time step T, similar to the diffusion policies that are conditioned on state S. The behavior cloning loss, denoted as LBC, helps the model jointly learn the contextual representation of the state and predict noise. This is done by minimizing the diffusion model loss, LDP, and state reconstruction loss, LR. The parameter lambda is a hyperparameter that controls the balance between two losses. Next, to guide the action generation process towards regions of higher rewards, we minimize the overall loss, LSRDP. This term also includes the behavior cloning loss and expected reward from Q function, which helps steer the policy towards actions that are more likely to yield high rewards. State reconstruction loss is propagated through the network for each diffusion time step, promoting learning more descriptive features from OOD state samples. Offline-RL dataset collected by a planner agent. In this experiment, we use an offline-RL dataset collected by a planner agent. This agent employs a PD controller to guide a robot from a random initial state to a random goal. The environment features a 2D force-actuated ball robot that navigates a closed maze, trying to reach a fixed goal during the evaluation phase. To assess SRDP's performance in OOD states, we use the missing large maze 2D dataset. In this dataset, certain key data points, particularly in the vicinity of 3 circles, including the goal and random initial states, are missing, making it a challenging evaluation scenario. This allows us to evaluate how well SRDP can handle missing information and still generalize to achieve the task successfully. Here, the table shows the mean and standard deviation of normalized scores obtained across 5 random seeds, indicating the importance of the state reconstruction loss in diffusion policies in OOD regions. NSRDP are the results for predicting the next state instead of the reconstructing the current state. It is important to note that SRDP with a bottleneck layer and scaling parameter lambda equal to 0 becomes diffusion QL with a state reconstruction decoder that without a state reconstruction decoder that further supports our claim. In this experiment, we designed a multimodal UR10 robot task. If the gripper here is open in regions A, red, or D, yellow, it should use the pink coffee stirrer and navigate to the coffee makers in red and yellow circles to stir the coffee. On the other hand, if the gripper is closed in regions blue or green, B and C, enabling the use of the green knife, the robot should navigate toward the vegetables in green and blue circles to chop them. The training dataset is constructed from the true positional commands of the robot's end effector, confined within the light blue rectangular region shown on the left. To evaluate the policies in OOD states, we sample states from within the black dashed line area. The action distributions are generated using the circular regions, constructing two Gaussian mixture model distributions. The first pair from circles in B and C, red and yellow circles, and the second from circles in A and D, green and blue circles. Here, we see the comparison of our method SRDP with the BC diffusion. Notably, BC diffusion memorizes the action distributions without effectively utilizing the state information. We evaluated SRDP and baselines, all trained with 75 diffusion time steps across 5 random seeds. The visual results are divided into distinguishable quadrants showing the performance of SRDP. In these quadrants, we can see accurate action generation for OOD states, which indicates that SRDP effectively generalizes. In contrast, the BC diffusion results reveal that it primarily memorizes actions rather than effectively utilizing state information. The table shows that SRDP with a lambda value of 1 achieved a chamfer distance of 0.071, demonstrating a strong alignment with the ground truth action distributions across the state region pairs. This result significantly outperforms diffusion QL with 0.27, emphasizing the importance of the state reconstruction loss. For those interested in further details, additional information on the D4RL benchmarks and 2D contextual bandit experiments can be found in our paper. In conclusion, we propose SRDP, a novel method designed to improve out-of-distribution generalization in offline reinforcement learning by leveraging diffusion policies and state reconstruction laws. We demonstrate that SRDP performs robustly in OOD states in our experiments. Compared to prior methods, SRDP excelled in 2 key areas: representing multimodal policies and partitioning the state space accurately, and achieving faster convergence in both real robot and simulated tasks. Our future work will focus on integrating a vision module to further enhance the system's capability and optimizing inference time for diffusion policies to improve overall efficiency. Thank you for listening.